Okay, so we're doing 7.2 here, and what you'll find is that 7.2 is very similar to 7.1. So we're going to fly through this pretty quickly. This should be a pretty short video because everything's the exact same thing, except instead of we're doing exponential growth, we're doing exponential decay, which means you can see down here that instead of a graph that looks like it's increasing from left to right, is a graph that's decreasing from left to right. The asymptotes work the same, the formula works the same, it's just that our A and our B are different. So if your A is greater than 0 and your B is in between 0 and 1, then that means your function will be an exponential decay function. And then the B is going to be called the decay factor. So before it was called the growth factor, now it's just being called the decay factor. And again, the only thing that affects this is when B is in between 0 and 1. So the idea of that is think about a power. Think about a fraction to a power. If you have a fraction to a power, when you multiply fractions by each other, they keep getting smaller and smaller. 1/2 times 1/2 is 1/4. 1/2 times 1/2 times 1/2 is 1/8. So that's the reason why it's a decay function, is because anything that's a fraction that's smaller than 1, it will continue to get smaller and smaller, which is why you get a smaller and smaller function. So just as a quick review, 0, 1 will be our y-intercept. That's if there's nothing in front of the b. Okay? And then 1 comma b will always be our first point. And again, that's affected if there's an a in front. This is the parent function of an exponential decay. So when we get into this, this is our b right here. And we have nothing in front of it. We have no a. So therefore, the 2 points that we're going to plot, and this is all we're going to do, is we're going to say 0 comma 1, and we're going to say 1 comma 2/3. And then when I plot that on the graph, what I'm going to do is I'm going to make this a little bit quicker today. We don't need to make a full table because we know what the general form of this is going to look like. We know that this is going to be an asymptote at 0. It's never going to touch 0. And this is just going in basically in the opposite direction. And our domain is going to stay the same. Domain for exponential functions is all real numbers. And our range, again, is dependent on where the asymptote is, because the asymptote here is at 0, and it's going to everything above it. It will be y is greater than 0. Okay, so basically the same thing that we were doing before. All the same rules. You'll see these notes are almost identical. It's just different words with dealing with decay and growth. So the same thing's true about stretching and shrinking it. Again, I'm not going to worry so much about that. I mean, the idea is just that it's going to either go up more rapidly or go down more rapidly. So let's just get right into this. So we have, the only difference about this one now is we have a negative in front. Now remember, the negative, all it's going to do is flip your graph. So all of our functions we've had so far are either doing something like this or doing something like this. So what's going to happen is that if we have a negative out front like this, all it's going to do is flip it below the y-axis unless there's a shift on it or anything like that. But it's basically going to flip over the direction of it. It's either going to go across and down, or it's going to go up and across like that. So that's the basic form of what it would look like if you have a negative in front there. So let's just go ahead and do this. We have the -2 out front. So again, the 2 only means that it's going to change more rapidly. But we still have our 3/4. So what we're going to do is we're going to plot our 3/4. And what's going to happen here is it's going to change where we start. Okay, so -2 times 3/4 of the x is not going to be above the x-axis anymore. It's going to be below. So what's going to happen is we're going to start below the x-axis. So starting below the x-axis, remember our a determines what our y-intercept is. So up here, the reason why we always started at 1 is because there is no a in this function. There's nothing out front. So down here, -2 is our a, so therefore our y-intercept is 0 comma -2. So that's our first point that we plot. And then our next point is going to be 1, but now it's going to be at -3/4 instead. Okay, so that's the one change about this. That negative really does affect it. So it's going to be 1, and we're going to say -3/4 Now, the only thing is that we are going to make one more change here, because when we put the 1 in and we get 3/4, we do have to multiply by our 2. Okay, so notice, normally it would be at positive 3/4 times 2, which is 1.5, but because it's negative, it will be negative 1.5. So our new point there is, again, I'm just plugging 1 in, so it's like negative 2 times 3/4 to the first power, so you have 3/4 times negative 2 is negative 1.5. So I'm going to plot my negative 1.5, and then again you'll see that this function looks exactly the same, except now it's below the y-axis. So when we define our range and domain, the domain is unchanged. It's going to be, domain is still going to be all real numbers, but our range will change. Our range, because it's below the y-axis, and again, it's approaching 0, but it never touches, so we're going to say y is less than 0 for our range here. Okay? So again, not much different. Again, it's just the way that the function is shaped, but it's the same general idea. So let's look at this next one. So anytime there's going to be a shift here, the way that I'm always going to show you is I'm going to give you the original. So our original would go through 0, 1, and then 1, 1/4. And this doesn't have to be perfect, but we'll get it as close as we can. That wasn't too bad, actually. So now that's our original, remember. So now what we need to do is, there's nothing out front, so our y values are not going to change except for the shift. So we have x plus 1, so therefore we're going to move to the left 1. Remember, the plus 1 means we move to the left, and the plus 1 out here means we're going to move up 1. So that means our new starting point will be right here, and then our other point will go up 1 and to the left 1, so we'll be at like 1 1/4. And we have a graph that looks something like this. So the same type of shape of the graph. I know that's not perfect. But again, now because we've shifted it, our domain always stays the same. It's all real numbers. But our range does change. And the range changes because we shifted the graph up 1. So now it never touches 1, and it's everything above that. So it's y is greater than 1. Okay? So let's move on to the backside. So here we have an exponential decay model, same as yesterday. The only difference is this negative sign right here. That negative sign was a plus sign yesterday, so decay just means you're subtracting what your percent decrease is. Okay? And I'm sorry, this should be, I didn't change it from yesterday's notes. That should be at 1 minus r. And so just, make that change on your notes. So that's 1 minus r is your decay factor, your a is your initial amount, your t is the time. So we're going to go right into this. We don't really have a compound interest for losing money, so we just use this formula right here, which is the same as we talked about in the previous section. So let's look at this example. It says, the value of a snowmobile has been decreasing by 7% each year. That's our decrease rate. Okay, the original cost was $4,000. That's our initial amount. 5 years, that's the time. Okay, so what is the value of the snowmobile after 5 years? Well, we use our equation. It'll be y equals 4,000, parentheses, 1 minus, don't forget to change your 7% to a decimal, which is 0.07, and then you raise that to the 5th power. You can put that right into a calculator, and you will see that the value of the snowmobile after 5 years, if it's decreasing by 7% each year, would be $2,782.75. And all you have to do is put that in a calculator exactly as you see it. Okay? Now the second one, that's a little bit more difficult. It says, how many years would it take for the value to reach $2,000? Well, 2,000 is going to have to go in for our y on this part. So in the second one here, put this in a different color so you guys can see it. We're going to put 2,000 in for y and set it equal to our equation. Now, we don't know how many years it takes, so we have to put our t back in for our variable, or our x, whatever. So here, we haven't really learned how to solve equations like this, but what we can do is we can use our graphing calculator. So here we are with our graphing calculator, and what's going to happen is is even though we had an equation that said 2,000 equals 4,000 times 1 minus 0.07 to the t power to the x power, what we're going to do is we're just going to put it as two separate equations. We know y is equal to 2,000. We know y is also equal to this equation. And then what we're going to do is we're going to graph it. Now, watch what I did with the window. I knew that my y max was going to have to be pretty large because we had y equals 2,000. And then I made my x max 50 so we could see the whole thing. So when I graph it, here's what our graph looks like. So we have our exponential function that's going down like this, and we have our y equals 2,000 going across like this. All we're looking for is this intersection point right here. So we go second, calc, 5. We're going to hit 5 because we want the intersection point. So what we do is we take this cursor and we get as close to that intersection point as we can on the first curve. Hit enter. It's already closed for the second curve. Hit enter. And then we hit enter a third time for our guess. And you can see that our intersection point is at x equals 9.55. So therefore, what we can do is we can state that our answer is after 9.55 years, because our x value represents our years here. So therefore, that answers our question because we found the intersection. So basically what we did was we found when is our function intersecting with the amount of money or the value of what the snowmobile would be. So, the idea of this real life problem would be like, you could ask yourself, if I bought something for this much and I know what the decay rate in the value of it is, you could say, okay, I want to be able to sell it when it's, worth $3,000. You can easily figure that out by setting $3,000 equal to your function and finding the intersection point. Okay, so that's all I have for this section. I will see you guys tomorrow. Hopefully this makes sense, and hopefully it was pretty easy like I thought it would be.